Right. So thank you very much for the invitation. I'm Marcelo Bertalmio from Universidad Pompeu Fabra in Spain. And I'm sorry I couldn't make it before. I had a previous commitment, and so I apologize. I would have liked to have been here since the start of this workshop. So I'll talk about basically my main research interest now, which is this. Can we shoot movies without artificial lights? And let me just clarify what I mean by that. Lighting, cinematography, is an essential part of making movies. So photographers, usually paint with lights. They use artificial lights to create a certain mood, an atmosphere. So you do want artificial lights to create this kind of scene, or this kind of scene, or this kind of scene, or this one, which I chose because it's the Turing test in Blade Runner. You do not want to get rid of artificial light in this kind of situation. But it's often the case that when you're shooting a movie, you have to use artificial lights just because otherwise you would not be able to see properly what's in the scene. So it would be not for artistic reasons, just for practical reasons. For instance, here you have this interior night shoot where you have artificial lights plus extra artificial lights. Or here, you just put lights there so you are able to see, or you let the camera, you help the camera to actually record what you want to be seeing. So what happens if you do not use artificial lights? Well, you get a dark image. Then you can think, well, let's boost it in post-production. So if you do that, you get this, which I think it's pretty obvious. You get a lot of noise. So this is a little original, without artificial lights. Then you boost in post-production, and well, you boost the gain, and that's a lot of noise. So the quality is poor. So this would explain why to use artificial lights in nighttime or low light conditions. But it's often the case that you have to use artificial lights also in daytime conditions. So this is a picture of taken inside a home. This is a living room, and it's taken with a short exposure time. Okay, so this is another picture taken with a slightly longer exposure time. Longer. So you realize that at the beginning we were able to see what's outside the window, and as we increase exposure time, we get to see what's inside, but we lose what's outside, which becomes overexposed. Okay? So by changing the exposure time, we can decide what to see, either outside or inside, but not both at the same time. And it's often the case that you will want, when shooting a movie, shoot a scene where you want to see both inside and through the window, outside. And if you want to do that, then you have to what you have to do is to add artificial lights. Okay? Why would that be? Well, the important concept here is that of dynamic range. The dynamic range of a scene is the ratio between the brightest and the darkest points in the scene. In this particular scene, the dynamic range is huge. It's around 7 or 8 orders of magnitude. Okay? So it's huge. And cameras do not have such a high dynamic range. So this is a chart of cameras, mostly, or all of them digital, from 2009. And you can see the dynamic range here expressed as the concept latitude, and well, you don't see anything here, but you will be able to check these slides if you want. So in photography, the dynamic range is expressed usually in terms of stops. So one stop is a halving or doubling of the exposure. Okay, so 10 stops, 9 stops, 12 stops. So this means that these cameras were able to record approximately 3 orders of magnitude of dynamic range. Okay. last year, cameras got up to 14 stops. Okay, so that's around 4 orders of magnitude. Much better. Still, not what we need for that kind of scene that is shown before. So, if you're shooting, so this is actually a frame shot with a in the digital cinema camera. Okay, the best camera around that it's used in most cinema productions. So, if you do not use artificial lights and you set up the exposure so that you can see inside the car, then outside is overexposed. Okay, like what's here. There's something. This is a window. There's something beyond that, and we don't see it. Or here, the exposure was set so that you could see the fire, but you don't know what's around here. It's a group of naked dancers. I will show that if you stay till the end of the talk. You will be able to see that. So, what to do? Well, you want to fit the dynamic range of the scene, very large, into the limited dynamic range of the camera. So, as the dynamic range was, as I mentioned, the ratio between the brightest and the darkest points, what you do is you add artificial lights. That brings up the dark levels. It brings them up, okay? Brings them up. So the ratio is reduced. So this is why you have artificial lights in daytime conditions, like here, or here, or here, or here, which is a bit shocking. People are wearing hats because they're on the beach at noon, and still they add this, okay? And this is a very important concept. Artificial lights in those situations are added for the benefit of cameras, not for the benefit of people, which were already pretty capable of seeing what they were trying to see. Okay? The dynamic range of human light perception is actually quite wide. Our human visual system is excellent in being able to grasp all this very wide dynamic range. So there's something we are doing that the cameras are not doing. So, as I said, this is a short exposure, one of us shown before, longer exposure, and we are able to see something like this, where at the same time we see inside and outside, okay? How was this picture created? Well, it was created in the following way. First of all, a radiance map of the scene was constructed. A radiance map is just an image which for each point has a value which is proportional to the intensity of the light arriving there. Okay? So, after building the radiance map for this scene, so creating the light, estimating the light which was actually arriving to the camera, then that radiance map was passed through a function called the Nacar-Rasten function, which models the response of photoreceptors in the retina. And this is what you get. Okay? Right, so how to create the radiance map? For still photography, the problem has been solved for almost 20 years now, and this is the de facto standard for that, the Debevec and Malik algorithm. So what they do is, from a stack of differently exposed pictures, they build this radiance map. How they do it? Well, they estimate the camera response function, which is unknown. So you just have the pictures. You don't know anything about the camera. Well, actually, you know something which is what were the exposure times? 1/2 of a second, 1/100th of a second, and so on. That's the only input. So they estimate the response of the camera from all the pictures and imposing, through optimization, and imposing some regularity on the response of the camera. It has to be smooth and monotonic. So after doing that, what they do is they use the inverse of the camera response function, and they average for each picture the estimate of the light. And what they obtain, so this is the input, okay, 16 or more pictures with different exposures, and what they build is the radiance map. Why is it in colors? Well, because the radiance map, the whole idea, the whole point of this is to create an image with a very high dynamic range. So here blue stands for 5 times 10 to the minus 3, and red stands for 121. So the order here, we have a very high dynamic range, which we cannot display because displays are also low dynamic range. So this is why we cannot display that. So you may ask yourselves, what's the point of creating a high dynamic range image when still you have to reduce it again to low dynamic range, if you want to display it? Well, the point is that if you build the high dynamic range image from your estimate of the light in the scene, then you can use a clever method to bring it down to low dynamic range, but keeping the details. So you create your high dynamic range image from differently exposed low dynamic range images, but then after performing that process of going from HDR to LDR, what you obtain is a low dynamic range image which looks good, it has details. That process is called tone mapping. So this method works under the assumption that everything in the scene is static, because this average doesn't take into account or assumes that everything is static. You have no motion neither from the camera nor objects in the scene. So if there's motion, you have artifacts, which is called ghosting. And there's a lot of work on doing high dynamic range imaging on non-static scenes. And this is one fairly recent work which provides very good results. Still, the problem is open. Okay, so in the film industry, there are several takes on high dynamic range imaging. One is used by the red camera, starting from the EPIC model. What they do is they use this alternating exposure approach. So for each frame, they actually take 2 frames. One with a short exposure and another with a longer exposure. Just 2. So this is the A frame, the X frame, and then combine them, okay? And do some tone mapping. The problem with this is that one frame, these frames are taken in sequence, so they're not taken at the same time. So you may have, and you do have, ghosting, which you have to, if the motion is small or slow, then you will not notice that. But otherwise, or often, it is the case that you have to post-process this to be able to actually show images without these ghosting artifacts. Another approach is to use the following setup. So this was published last year by researchers from ARRI, this company that manufactured cameras. They were complaining about the quality of existing high dynamic range video sequences for benchmarking. They complained that they were bad. So they created a new set of high dynamic range video in cinematic conditions. So they use good cameras plus directors of photography and many different conditions, and actors even, and the images, these sequences that they created really look good. How did they do them? So this setup, you have here 2 cameras, one camera here, another camera there, okay, and this is a semi-transparent mirror, okay. So you have light coming in here. 94% of the light goes to this camera, and 6% goes there, okay? And they're perfectly aligned. So they take frames, they're synchronized, and they take frames at the same time, okay? So you have one camera producing this image and another producing this other image, okay? So the good thing about this is that you do not have ghosting. And by this method, they're able to create high dynamic range video with 18 stops, like 6 orders of magnitude. It's pretty high. Right, so as I said, from the high dynamic range images, you have to go to low dynamic range images for display. And how to do that? Well, you have to do it properly, otherwise things do not look right. If you use linear scaling, this is what you get. This is one high dynamic range image, linearly scaled, where you assign 255 to the brightest pixel and 0 to darkest. So you see nothing. There are a few white dots there. You see nothing. Why? because most of the pixels are very dark and you have just a few very bright. So linear scaling produces this awful result. This is what you get with a tone mapping that does local histogram equalization. This is one approach. So this is what you get. So the way you do tone mapping is really important. So the following images were I downloaded from Flickr, and what you see, at least in Flickr, is that most tone mapped high dynamic range images do not look realistic. So in some cases that's on purpose because they want to produce some artistic effect, like here. In some of the cases, it's just that they could not find a proper tone mapping algorithm, and you get halos and things that do not really look realistic. And you, this is very extreme, but you also get that in the for instance, with this film industry solution of the red camera. So this is what you get. So short exposure, long exposure. I'm sorry, this is just a mixture, okay? And it looks a bit washed out, so they have to increase the contrast, okay? Like a post-processing step, which means that their tone mapping is improvable, okay? So this is an excellent book on high dynamic range imaging. The literature on tone mapping and high dynamic range imaging in general is vast, and this is a very good book that overviews and, well, details all the concepts. I highly recommend it. So a few years back, we proposed a tone mapping algorithm which was based on human visual perception, and it consisted of two stages. In the first stage, we approximated light adaptation following Weber-Fechner's law in the pulsed condition. I will not go into details over there. So this result I showed before used the Nakarshan equation, which models the response of photoreceptors in the retina, and this is what we get with this method that we proposed, where we are following, instead of the physiological response, the perceptual response. So you get to see more details and still looks natural, which is the point. And the second stage of our method was a contrast enhancement stage. So here they're just examples of the error distortion estimated using the DREAM metric by Aidin and colleagues from the Max Planck Institute, a very very good perceptual-based metric for high dynamic range imaging. So so this is the one result, and this is the error measured with this metric, and all the colors, green, red, and there's a little blue, indicate error, and gray indicates not error. So this is the output of the first stage of our method, and this is the output of the second stage with the local contrast enhancement. You can see that from here to here we reduce a lot the error. Another approach for producing tone mapped images with low error is to just minimize that metric, okay? Minimize the DREAM metric. The DREAM metric gives you an estimate, a per pixel estimate of the error. Well, you minimize that metric. It's a very computational intensive procedure, but you can do it. And it's actually, and also, it's tone mapping algorithm agnostic. So it does not depend on the algorithm that you use. So you choose your favorite tone mapping algorithm, obtain a result, and then you apply our minimization, and you get an improved result. Okay, just by minimizing that metric. Okay, in a very recent work, we studied the following. We studied the following problem. We showed observers images, and we asked them to rate them, how good they look to them. Okay, and the model was that you show radiance map, linearly scaled. It goes to something which is called the, it's a power law, gamma, the system gamma. The system gamma is the product of two gamma values for two different power laws. One is the encoding gamma applied by the camera, the recording equipment, and the other is the decoding gamma applied by the display. Okay, the product both is the system gamma. So that produces on-screen luminance, and that goes through our human visual system, and we approximate our perception of lightness through this another value, gamma psi, which is around 1/3. And this is the perceived lightness. And then we estimate the flatness of the histogram of the resulting lightness image. Okay? And what we observed was that image quality is possibly correlated with the flatness of the histogram, meaning that we tend to like more images whose lightness have a flat histogram. Okay? That are equalized. Also, in recent work from last year, I proposed an extension of neural model equation, which is related to local histogram equalization and to efficiency of representation in the visual system, and which allows this new model to reproduce visual perception phenomena called visual induction. Induction is the effect by which the way we perceive an object is affected by its surround. Okay, with this couple of developments I just mentioned, we recently proposed a new tone mapping operator, which also has 2 stages as the one I presented before. And the first stage of this operator is a gamma transform, which flattens the histogram the most. And the second stage is this new equation that allows to reproduce visual induction phenomena. So with these 2 stages, we obtain tone map images like this. They come from the high dynamic range database of Fairchild, standard still image high dynamic range database. Excellent. So this is our result with the distortion map. This is by a state-of-the-art method by Mantiuk and colleagues, another state-of-the-art method by Reinhardt and colleagues. So what we are currently working on is the following. We want to perform nonlinear correction in camera, which is based on perception, on perception data, perception results, and which allows to do tone mapping in camera and produce images that look natural. So one thing to bear in mind is that in the eye, there's a lot of degradation to the light coming into the eye. So light comes into the eye, goes through the lens, and it's scattered. And the end result is that the image formed on the retina, you can model as the incoming light passed through a point, convolved with a point spread function which has this shape. Okay? So the net effect of that is that if this is the original image, this is what you would get as retinal image. This is not what we see. What we see is something like that. This is what is captured by the photoreceptors. And we'll present this in the summer. We did the following. We took the high dynamic range Fairchild database of still images, passed it through this point spread function, which represents the spread function, the PSF of the eye, modeling scattering and aberration. And what we got was this kind of data, which just look at this one. So this is the world dynamic range, and this is the retinal dynamic range. So even if the world dynamic range goes to 10 to 6 orders of magnitude, the retinal dynamic range goes often below 4. So the retinal image has already a reduced dynamic range. There's a very good survey article from last year by Pablo Artal, in which they explain that there's evidence that the human visual system is actually improving the image that is captured at the retina. So there's the convolution and contrast enhancement going on that improves the quality of the image. So, taking this into account, what this inspired us in the following manner. We thought, well, if the image at the retina level has a dynamic range which is compatible to the dynamic range which a state-of-the-art digital cinema camera can capture, well, maybe if we propose processes that emulate how our visual system works, then we can get an image on the camera which is equivalent or similar to what we can actually see or perceive. So we used some other stuff here. This is classic work by Huang and Mumford. So this is the statistics of natural images from some standard database. So this is the log histogram, log luminance. You can see that this is the average behavior of natural images. So from this, using also this result that I mentioned before, that we prefer images with flat lightness histogram, and using also this excellent review paper from 2-3 years ago, in which they show that contrast normalization is a process that goes on at every possible level in our visual system, from the retina through the thalamus to the visual cortex. There's all the time normalization procedures. And so using all this, we propose a new model which we apply to the raw images, raw meaning at the sensor level, without any processing from the camera. And we get the following. So this is the output of the camera. So from the raw, all the processing done by the camera, we get this. If we, instead of this, we take the raw and apply our method, this is what we get. Now we are able to see what's outside. Likewise, this is what you get from the camera, and this is what you get if you apply our method to the raw. And also, this is taken with a consumer camera. So that was a JPEG. And this works on videos as well. So this is one of the 18 stops videos created by in the ARRI dataset that I mentioned before. So you can see that the whole point here is that it has to look realistic. Not only you have to see details, but it has to look realistic. So this is what's going on in the very dark scene now. You can see that. There's no artificial lights here. I mean, only the welding and the fire, but there's no lamps there. Okay, that's the whole point. And in the previous sequence, there weren't any lights here either. And finally, I like this sequence very much. There are artificial lights there, but only because they were proper in the scene. So you did not need to carry around lamp equipment or anything. So references, most of what I've mentioned is you can find in my book, and this is the publication in our publication page in our website. This is work done with my PhD students Raquel Gil, Gabriela Gimpeteanu, Pravin Siriak, and Sayed Samir, and my postdocs Gigi Kim, Thomas Batard, David Kane, and Javier Vázquez. I have to acknowledge support by these very fine public institutions, ERC through a starting grant, the Spanish government, and the Catalan Institute for Advanced Research. And this is our website, and thank you very much.